this series of talks, as I said a couple of weeks ago, probably before the first talk, so the middle talk was on connection with model theory, and in fact, the other two talks, both on growth and today on automorphisms, will be on or are on application, not on results for model theory, but some of the techniques that were originally developed for techniques and concepts that were originally developed for studying formulas and sentences. So for model theoretic purposes, to study objects and questions that we study more often in group theory. And today I'll try to present my approach to study automorphisms. Okay, I'll get to explain in what context, but somehow the techniques will be, and the concepts and the whole strategy, the whole approach will be influenced by techniques that were developed for a completely different reason, as I said, in connection with model theory. But no, there will be no model theory in this talk. So I'll start with with the origin of the JSJ decomposition. So the work of J. Koshelin and Johansson in the, I guess, mid-70s, the second half of the 70s. And what they found that in every three manifold, this will be, okay, what I need is for three manifolds with boundary, there's some canonical collection of cylinders that may be empty. And okay, the manifold may have boundary. Oh, well, actually, from what I'm drawing, it always has boundary. Okay, so there will be also parts which are surfaces cross I, or rather I bundles over surfaces that somehow, this was called the characteristic submanifold, that in a way carry all the properly embedded cylinders, properly embedded annuli inside the manifold. And I think this was mostly the contribution. I mean, this mostly appeared in the work of Johansson and less in J. Koshelin, that it was also possible to understand from this characteristic submanifold, this in the Haken case, this group of the homeomorphism modulo homeomorphism that are isotopic to the identity. Okay, so it's possible to understand the structure of this group from the characteristic submanifold. Later on, okay, and this will be more relevant for my talk. Okay, now we restrict first to hyperbolic groups. So if gamma is a hyperbolic group, so it's possible, even with this decomposition, it's possible to associate a graph of groups decomposition just by basically applying the Van Kampen theorem and using the connected components after we cut along these cylinders. So there is the JSJ decomposition of the hyperbolic group, which again may be trivial, but if it's not, and here the group may have torsion. So these are orbifolds, in fact, finite extensions of orbifold. Okay, anyway, some graph of groups, and this is a canonical graph of groups in this context that, in particular, encode the automorphism group of the autoautomorphism group of the hyperbolic group. So if we look at out gamma, the autoautomorphism group, and okay, at least for now, it's not really necessary, but we will assume that the group is one-ended. Okay, so it means that all the edge groups in the JSJ are virtually cyclic. So it's possible to get a short exact sequence for, in fact, not for the whole autoautomorphism group, but a finite index subgroup of it. Okay, so there is a finite index subgroup of inside the autoautomorphism group. In fact, elements in the autoautomorphism group in general will permute perhaps the vertices here. Okay, so we look at all these autoautomorphism that the action as a permutation is trivial, is the identity, and okay, this goes on to the direct sum of the mapping class group of the why do we do two? Okay, the mapping class group of the of these orbifolds. actually it's finite extensions of orbital, but it doesn't matter. So this is onto, and the kernel is virtually a billion, virtually finitely generated a billion. Okay, and from that you see from this short exact sequence here, okay, as I said, the map is onto. It's possible to deduce both the dynamics of automorphisms and the algebraic structure of out gamma, which essentially reduces to that. The algebraic structure essentially reduces to the mapping class groups, and the dynamics essentially is all obtained from the work of Thurston or whatever came afterwards. Anyway, on surfaces. So in some sense, we don't get anything new. There are extensions of this to when the group is not one-ended, and then we have to add things, to add what we know about free groups, about free products. But essentially, everything is encoded in these decompositions. Now, the JSJ was later generalized to all finitely presented groups. But there are several versions of that. It doesn't really matter. But what's important for my talk is that there's nothing like that, and there cannot be anything like this for a general finitely presented groups. So in general, you know, if we have a graph of groups like this, the JSJ of a finitely presented group, well, we can let alone the fact that there's a problem with the JSJ being canonical for a finitely presented group. But we'll put this aside. It's impossible in general to read off all the automorphism of the group from the structure of this JSJ decomposition. Okay, in particular, the automorphism can be infinite, but this graph can be trivial. So in general, for finitely presented group, the JSJ decomposition in each of its version, it doesn't matter, encodes some family of automorphisms in general, but not all of them. Okay, and we cannot expect it to encode all of it, all the automorphism. There cannot be any graph of groups like that. Okay, now what I want to talk about today, again, I'll get to that in a few minutes. I want to talk about a generalization of the JSJ decomposition that will be good for products of hyperbolic spaces, and more generally for HHG, for hierarchically hyperbolic groups, with two extra conditions that anyway the mapping class group have. But I'll get to that. But before I'm going to do that, let me just present another point of view, which will be important later, just on automorphisms in general. Okay, that will bring us close to why it's connected to questions that originate in logic. Okay, so we can view. Okay, phi is an automorphism of, say, a group G. Okay, phi is a map from G onto G, and of course it's also one-to-one. But in particular, phi is a homomorphism. So we can look at the collection of all homomorphisms from G to G. And the set of all homomorphisms from G to G, well, if G, okay, in our case, G is finitely presented. That's not particularly important, but let's say G is finitely presented. So G is generated by some presentation with a collection of relations. And homomorphism from a group to itself, okay, another way to think about it, we can associate with G a variety, Vg. Okay, let me put it here. Okay, this is the collections of all values to some variables, x1 up to xn. Okay, this tuple, so that all the relations hold as equations. So this is a tautology that the set of homomorphisms is equivalent to points in this variety. Okay, these are all the tuples that satisfy the relations as equations. Okay, just that you know, automorphisms are very special homomorphisms. These are homomorphisms that satisfy they're both epimorphism and monomorphisms, and this cannot be, you know, both the condition that a map is epimorphism and monomorphism cannot be expressed as somehow equalities or inequalities, or even any first order formula using this variable. Okay, this is in logic they call it a transcendental property. Okay, it's not algebraic in any way. Now, okay, I'm explaining this because I'm going to use it, and I'm not sure. There's some people here that know these things very well, but I cannot probably assume that people are familiar with these things. So, okay, let me do it here. The thing is that to understand homomorphisms in general, homomorphisms say from gamma to G, there is a general formalism to describe that, just that it doesn't work for all groups. It cannot again. But say in the case that G is hyperbolic, but much more general than that, maybe now there are a lot more general works on that. Maybe I'll mention some later in connection to what I'm going to talk about. But homomorphism from gamma to G, okay, in particular when the target is hyperbolic, this can be any finitely generated group, are encoded by what's called the Makanian-Rasborov diagram. Let me just say a few words on that. Okay, so well, we start with gamma. And this setup, gamma has finitely many. Here it's a canonical collection of certain limit quotient. Okay, it doesn't really matter now what it is. So let's say Lm. Okay, which are not, if G is hyperbolic, these are not hyperbolic groups anymore, but still they have a lot of structure, a lot of geometric structure. And each of these L1 to Lm have JSJ decompositions. And with this JSJ decomposition that is drawn over there, one can associate a group of automorphisms, okay, the modular group of automorphism. And we can use that to proceed further to some other limit groups, let's say M1 to MR or something, etc. And we understand where this diagram terminates. It terminates after finite time deconstruction. And we understand well what are the terminal limit groups. Okay, I won't describe them now. But you see, there's a big difference between automorphisms here and homomorphisms. And this is important conceptually, not just technically. Homomorphism can be described only by some hierarchical structure. It's impossible to describe them in one level, just impossible. On the other hand, somehow miraculously, automorphism can be described by the decomposition that appears in only one level. See, this is one decomposition, and it encodes them all. Okay, and this was a big question when one goes to some other class of groups. If something like this will be true, whether the description will be by some hierarchical structure. By the way, it's a different hierarchical structure, but hierarchical structure is also essential when one talks about automorphisms of free groups. But in one-ended groups, here it's just one decomposition in one level and describe it all, like the three-manifold picture. So this is a big conceptual question whenever any of these techniques can be applied, whether the object, the structure of well, okay, we study automorphism, whether it will be hierarchical like this or in one level over there. Okay, and it's not at all clear why things should appear in only one level. Okay, let me, I'll get more specific. So actually, I started this question with this project with the question of Ilya Rips, and the question of his was, what can one say about out of pi 1x when x is a finite locally equals 0 cube. So, for this, of course, when the group is hyperbolic, that's not an interesting question because for hyperbolic groups we already understand the question. But in general, what can one say about the automorphism of these fundamental groups of cube complexes in general, non-positively curved cube complexes? And to try and answer, at least partially, this question of Rips, okay, I moved to a class which, in some sense, generalized this, but not all cube complexes have this property. Anyway, to the class of HHGs, which will not be, okay, again, this is a notion that, probably not everyone is familiar with, and I'm not going to use it, that everything although everything that I'm saying applies to that. Okay, so this is hierarchically hyperbolic groups, and they were introduced by Burstock, Hagen, and Sisto. In the last decade, I said, I guess. And their attempt was to basically axiomatize properties of the mapping class group, but it turns out that this axiomatization is very, very helpful. You see, like, from my point of view, to study automorphisms, it's, for me at least, it was much clearer to look at these cut zero cube complexes as HHG, rather as to think about them as cube complexes themselves. Okay. Well, of course, it's not clear that this is the right approach, but anyway, using this approach, one can look. This question of Rips becomes much clearer, and that's what I'll try to explain. But again, I'm not going to get into any of the details of these HHGs. The definition is very technical. So I don't see also a point to try and get into that, though everything that I'm going to say applies to them. Again, as I said, with 2 extra conditions, but I'm not going to mention them either, that anyway hold in many cases. But you know, to make things simpler, I'm going to look at a particular example that, to my understanding, most of the problems appear already in this case. And if one knows how to deal with this case, then you know, this is technicality. It's not trivial, but there are tools to generalize them to HHGs in general. So there's no point to try and explain what happened with the general HHG. Okay, and the case that I'm going to look at in the beginning, it may look simple, but it's not. This is the case of, as I said, products of hyperbolic spaces. So, you know, and anyone who works in group theory after sometimes, I'm sure, sees that products in general cause a lot of difficulties, a lot of pathologies. There are many examples that were constructed by some people in the audience as well that uses pathologies of products to construct all kind of pathological examples. Subgroups of products are usually very difficult to study, so it's not at all easy. But what we are going to study is groups that act on the product space. So X1 to Xm. Okay. This will be X to X1. Okay, and I'm going to explain why this is connected afterwards to study of homomorphism. So why it helps at least. Okay, so I'm not going to consider all actions, but I'm going to consider action as which are part of this HHG machinery. So we will also assume that that this action on the whole space restricts to action on each of these spaces, but no, I should say that okay, the action G of Xi may again be X of sigma. Let's say we'll call it like this, sigma G of I. It means that every element can permute these spaces when it acts. However, we assume that okay, that for those elements that the action of G on the factors actually preserve distances. It means that it's isometry. In other words, you know, we can always pass to a subgroup of finite index in G, in fact, a characteristic subgroup that preserves the factor. And now this H acts on each factor isometrically. It's possible to slightly relax the condition, but this doesn't matter. Okay, so we have a finite index subgroup that, of course, acts on the space as a subgroup of finite index, but it also acts isometrically on each of the factors. Okay, it acts by projecting each point to the factor. Okay, and we want to, as I said, the goal is to understand the structure of the automorphism of a group that acts on a factor. See, the group itself in general will not have product structure. It just acts on a product. We want to understand it's okay. What can one say about this out of G And you know this out of G, or let me put it like this, out of G acts on H because it's characteristic. Okay, so we are going to use the action of the automorphism or the automorphism of G on this characteristic subgroup H. Okay, so let me explain what is the goal, first of all, of this study. Well, we'll start with the partial goal. Okay, so we want, again, the big question was, you know, even if we have this type of techniques, whether it's possible to describe the automorphism by some diagram like this, which is hierarchical, or by something which is similar to the JSJ, which is only appears in one level. And okay, it took me quite a time to decide what's the right option. Of course, describing in one level is much more powerful, also for applications. Okay, describing automorphism or encode automorphism by just splitting is much more powerful for application, I think. So let me just do it schematically. Okay, these are the factors. Okay, just do 3. Okay, so what we are going to, the goal that we are, what we want to construct is the following. We have this group H, finite index subgroup. Nothing will be dependent, by the way, on the finite index subgroup at the end. So, you know, to what finite index subgroup we move, that doesn't really matter. But with each factor, we are going to associate, let's say here M1, some quotient of this group. Okay, so proper quotient or not, but anyway, quotient. And this quotient will have some sort of decomposition, which is JSJ-like. Okay, so in some groups will be virtually abelian as well, or can be. Okay, now, okay, this is H mod some N2, etc. M3 will be H mod some N3, and each of them will have their JSJ-like decomposition. In general, there's no connection between the different decomposition that are associated with different factors. Okay, so each factor will have its own decomposition. I should say that, you know, part of the problematic with all this whatever question or branch or whatever is that well, these groups are not canonical, or at least I don't know why they should be canonical. They are not canonical for G, yeah. It's some normal subgroup. What action? See, there's no, it's not. No, it's not the kernel of the action of H on Xi. No, if that's what the question, then definitely not. No, that's again, this is part of the problem. These groups are not canonical. The kernels are not canonical. The kernels in general are not invariant under the automorphism group. I mean, this is very different than working with the hyperbolic group when we don't have problems with kernels at all, just the group itself. Okay, these are automorphisms, they don't have kernels. Here, the kernels are not invariant by the automorphisms in general. And this is a big problem. However, okay, I said that nothing is canonical, then, you know, what left? No, but the structure of the graphs is canonical. So the surfaces that appear here, you know, the number of edges, the virtually abelian groups, all this is canonical. And from that, it will be possible, I mean, somehow, again, this is also, you know, somehow the fact that the groups are not canonical is in a way, it appears in places, namely this vertex group over here, in the rigid vertex group, that are not so important for understanding automorphisms. So somehow the non-canonical parts, which cause problems, it's not okay. It's both from technical and conceptual point of view, these are not, it's not something negligible. However, what's responsible for the automorphism, these pieces are canonical. And as I said, okay, I slightly cheated because in general, it will not be just quotient of H, but okay, I'm not going to get into this. But the surfaces that appear here and the virtually abelian groups, all this does not, that doesn't, so these are canonical. They don't depend on anything, basically. Of course, they depend on H, and yes, but not on the construction itself will always lead to the same, these parts will be identical. Okay, so it's like you have a JSJ, you don't know that the rigid vertices are the same, but you know that the parts that somehow encode the dynamics of automorphism, and in a way the algebraic structure of the automorphism group, these parts are canonical, the other parts are not. And in some sense, they are less important. But when you work, when you construct these things, you have to, of course, you have to face that there are the fact that there are parts that are not canonical, and you have some control on them, but definitely not full control. Okay, so let me. Yeah, I also didn't explain what's the connection between the automorphism group and this. Now we have, I call it a higher rank JSJ decomposition because there's a JSJ decomposition for each factor. Okay, and for those that are familiar with HHE, those that are not, it doesn't matter. Okay, for those that are familiar, for HHE in general, I also assume that the JSJ is colorable. Okay, so there are finitely many orbits under some finite index subgroup that each projection spaces, or each domains in these orbits are transversal. And well, there is a JSJ then for each such orbit. So again, there will be finitely many JSJ decompositions, like here, basically. The construction is, as I said, is more technical in general. Okay, so let me explain now the strategy, and I want to connect it with homomorphisms, as I said, and
product of rigid groups and
no, the rigid groups are not in the NIs, yes. The rigid groups are part of the quotients.
NI generated.
Well, NI in general is not, it's not finitely generated in general. This is some normal subgroup. As I said, it's not canonical either. Okay, I can say later, but something about it. But I definitely don't know. I mean, it's not unique or anything. It's okay. So let me try to explain why this point of view of varieties is really helpful here. See, the constructions of the JSJ that we are familiar with, either from automorphisms or from complexes of groups, or well, okay, there are some other ways to construct it using Dunwoody's tracks. They will immediately tackle problems because all the actions here have kernels. And as I said, the kernels are not invariant under the automorphism a priori. So all of them will tackle difficulties. I don't know to apply any of them to get. Okay, so one needs some other approach, both conceptually and technically. Okay. So what we look at the homomorphism from H to itself. Okay, so this is a much bigger set, and in this set, this collection of automorphisms. Okay, this is out. I'm really suggesting the automorphism of H, which are really automorphism of the ambient group G. Okay, and what we want is we're not interested, but it's possible also to give a structure of all homomorphism that makes to itself. This will be some diagram, the hierarchy, so the hierarchy, no way around hyperbolic, even hyperbolic groups. What we want to understand, just the collection of automorphisms. Generalization and then that inside, we need to explain why somehow they use the self-accidental in a way it's more simpler structure than the structure of the variety or the home. It will explain also from a different way why we get something which is only in one level, of something we want to improve and forcing. Whereas for homomorphism, we need all these and somehow the way that we are going to go is the original way to start a form diagram. Use the JSJ to write that. Use the modular group, the automorphism, which limit group to the interior and simplify things. So one start one diagram. Here we don't have JSJ, but we can construct the diagram. We want to go in a reverse order. We want to construct the diagram, then the diagram will not be canonical in any way, because we're going to use compactness to construct the diagram. But then we want to exhaust canonical information about automorphism from the diagram. Okay, and somehow to obtain this JSJ higher ranking. Okay, so and this is also, I should say, this is also some sort of idea that I got from logic. There are problems in logic that they solve that require a description not of a variety, but of a definable set. Now, definable set also, the definable set is something that is defined using some formula. This is not true for automorphism, but a definable set in general has geometric structure, but it's much more difficult than a variety. Okay, it's defined by a much more complicated formula. Still, for some problems in logic, one doesn't need to understand completely what's this definable set is, but you just want general properties of it. And for general properties, it's possible to associate with a definable set. Now, a general definable set, some structure, which is similar to structures of varieties, similar to these diagrams, and it's enough to work with that. This is what I'm calling the envelope of a definable set. So what we are going to do now, we are going to basically construct an envelope of the set of automorphism, okay? But we are going to really get the structure of automorphism, unlike a definable set. Okay, so, well, how are we going to do that? First, we start only with automorphisms and not with all homomorphism, only with automorphisms. Okay, in some sense, hoping to get something which is much stronger than the structure of all homomorphisms. So to do that, first we construct, as I said, a diagram like this. So from each factor, and here we work with the factors separately, each factor in parallel. See, the big problem with product spaces is that it's many times it's possible to work with each factor separately. The problem is how to put them together. I mean, even if you think, if you go really far, if you think about the Poincare conjecture, this is the major problem in the algebraic formulation of the Poincare conjecture. It talks about an epimorphism from a surface group to a direct product of two free groups, and it's possible to analyze each of the epimorphisms separately, but putting them together, well, we still don't know how to do that. And there are good reasons why we don't know. Okay, so this step we do separately. Okay, this is one step that we do separately for each of the factor by itself, but then we again put all of them together. Okay, so with each of them, what we associate is what I call a resolution, a path in this diagram. So this will be, say, L11, L12, etc. Until L1, say T1, and okay, here it's LM1, LMTM. And okay, so we construct, I'm calling it M collection of resolutions. And using a compactness argument, it's possible to show that we need only finitely many such. Okay, so this is the analog of the Makarian-Rasborov diagram. This is a Makarian-Rasborov diagram in this context, which I'm calling a high-rank Makarian-Rasborov diagram. So there's finitely many M collection of this resolution, which is built just from automorphism, not from general homomorphism. And every automorphism phi belongs to to our G, then this phi must factor, or if you want somehow the projection of phi to each of these factors, must factor through this one of these M collections of resolution. So anyway, this collection of resolution, which is the analog of this diagram, somehow encode all this automorphism. Of course, it's encode a lot of other garbage that has nothing to do with automorphism. But at least it encodes all the automorphisms. And the way to construct that is using compactness. Okay, I'm not going to explain that, but because basically we don't know anything. The only thing we can use is compactness, using some descending chain condition on these sequences. But the disadvantage of using a compactness argument that if you use compactness, the output cannot be canonical in any way. Okay, it gives us some finite M collections like this, but we cannot expect any sort of canonical behavior of what the output of the compactness argument is. Okay, and the question is how to obtain this at the end. First of all, these are only one level, and also this decomposition. What we want from them is that the parts that are responsible for the automorphisms will be canonical. Not everything, but the parts that somehow encode the automorphism will be canonical. Okay, and we want now some sort of procedure that start from these diagrams that again is an output of some compactness argument and somehow exhaust from it canonical information. Yeah.
I mean, if the automorphism of G, or let's say of H.
Okay.
So X1 is an automorphism of
No, X1 is one of the factors. Okay, X
sequence. And L11 to all the way to L1 P1. This is an automorphism of the image of H.
It's not right, but it's not an automorphism, but okay, but you see where to write it. Right, H act on X1. So we can twist the action by phi. Okay, and that's what it means, that the twisting of the action, okay, for each.
And if the action is faithful on X1, then this means that this sequence is terminated after one step.
If the action is faithful, we can arrange it to stop after one step. Yeah, that's true. It's not the way it's built is not exactly like this, but it's possible to arrange it. Yeah. Then okay, in this case, in this case, if the action is faithful, then you know, whatever you will read is dominated by the JSJ of the group. But here you have no idea what these quotients are to start with. Okay? It's going to find them, and again, they are not canonical. Okay, so how we continue from here, or how do we find these canonical objects? Okay, now we work, as I said, to construct these resolutions. We work on each of them separately, but now we work on them as collections from now on. Okay, and okay, what we are going to work with in order to construct this resolution, these sequences, we work with sequences of automorphism. Okay, where each of Ts belong to G. Now, okay, let me just explain it in principle. If we take now any automorphism tau in G, a fixed one, and we look at phi s composed with tau, this is another sequence of automorphism. And this sequence of automorphism must factor, because you know our collection has this universal property that any automorphism factors through them. So this sequence of automorphisms, if we pass to a subsequence, it will factor through another collection. Okay, and using that, okay, using the fact that this factors through one M collection, and this factor through maybe the same, but another M collection, but there are only finitely many of them. Okay, we construct a map that we call mu tau. Now it will be a bit difficult for me to explain from what to what is this map, but I'll try to say a few words. Okay, there are people who are familiar with this thing. See, with every resolution like this, it's possible to associate. This is canonical construction, some tower. Okay, that I'm calling a completion, but it's possible to anyway. It's possible to associate some group with each of them that has some sort of tower structure. So it's very geometric construction, and this mu tau is a map from the tower. This is associated with with the collection that this one factor through to the tower that that is associated with this thing here. Okay, and after a process that modify actually the whole diagram, this map can be made geometric, and there will be surfaces along this, and maybe virtually a billion group along that. And this map, okay, after we modify the whole construction finitely many times, what this map will do, okay, it will preserve the geometric structure of these two things. So it will map surfaces here onto surfaces here, virtually a billion groups here, onto virtually a billion groups here, etc. And essentially these groups and the splittings that we read can be read off from these towers here. So at the end, we are left, okay, after we exhaust the information, we are left with a splitting or a quotient for each factor. I should say, okay, let me just say one word one additional words on that. Okay, this is a rather technical construction, so I'm not going to get into detail. But you know, when you get something out from a compactness argument, you cannot expect that all the collection that the compactness argument gives as output will be helpful. But the hope, and that's in reality that's what happens. One can hope that somehow those collections that have the highest complexity, or you know, if you think about it dynamically, the highest entropy, these ones, okay, those that have the highest entropy, these ones are the ones that are going to be invariant, and that's what happens here. But even the highest entropy one needs some. It takes finitely many steps in order to somehow modify them. But at the end, it's possible from these towers to actually construct these JSJ decompositions that are associated with these factors. And I already said what are going to be their canonical properties. They are not canonical. The groups themselves are not canonical, but the surfaces, you know, the virtually abelian groups, etc. These are canonical parts. The number of edges that appear, the edge groups, these are canonical parts. No. Okay, no, mu tau. Okay, mu tau is a map. Okay, it's precisely what I wanted to skip. So mu tau is with each such resolution, it's possible to somehow functorially or canonically associate a group that has a tower structure. And it's it's a geometric map between groups. Okay, this group is composed. There are surfaces or orbifolds that appear along the levels of this group. They are virtually abelian groups, and this map will preserve the level structure and the geometric structure, at least in the one-ended case. If it's not one-ended, one needs to say a few more things.
So it's really a product of towers because you have this.
Yeah. Well, okay, I better say it's finitely many towers. And okay, the map will be okay from the J tower here to the J tower there. Okay, so let me, what I didn't say yet is what is the consequence for the automorphism group. So unfortunately, these things, I think I spent most of the time in this work on this last thing. Yeah, I spent a lot of time also to decide whether it's hierarchical or not. But okay, let me. So this is something that I changed my times. I don't know my opinion. I think dozens of times, but still, at least I didn't write the proof of that. So I'll state this as a conjecture. But okay, but now I think that, and say a few words on it. Why I think that this is true, and one can even prove that. So this will say that, see, very similar to the picture in hyperbolic group. So we have here, okay, the outer automorphism of G. Again, we have to pass to a finite index subgroup. That's always true because the whole outer automorphism group can permute certain things. So after permutation, after we mode out this permutation, we are left with finite index subgroup. Now here it will be not a map onto, but a map into the direct sum of the mapping class group of the orbifolds that appear in all these JSJ decomposition that are associated with all the factors, and the same thing for HG. That doesn't matter. Direct sum with outer automorphism group of virtually abelian groups that appear here, okay, as vertex groups, and the kernel should be finitely generated virtually abelian. Okay, so it's a very similar picture to the hyperbolic case. Okay, just the difference is that here, well, one cannot claim that this map will be onto. This is just into. Okay, and again, one can say a lot about the dynamics of individual automorphism just from what we know about surfaces. There's also, these groups of the general linear group. So we have to take this into account as well. It doesn't appear in hyperbolic, but here it appears. Okay, and this is just well, the kernel is just virtually abelian group. I don't have to say much more about this. Let me just say, just as maybe as a conclusion, see the JSJ itself, although it was generalized to finitely presented groups, it is really a rank 1 phenomenon. One sees here very well this picture. See we work here. Let's look again at the example of this product space. We don't see somehow the dynamics of automorphism when we look at the higher rank picture. Okay, we see the dynamics of automorphism well when we project it to the factors. Okay, so for example, these surfaces, you don't see them if you look at the higher rank picture. You see them only in the rank 1 picture. Okay, it's somewhat different than the concept of Danny in his seminal work, that to study free manifolds you have to go to a much higher dimension. Here, to really see the dynamics, one has to go down to rank 1. But still, okay, to gain some of the information, like to construct this short Dirac sequence, one needs to work somehow in coupling between the rank 1 picture and the higher rank picture. But again, the dynamics itself is all concentrated in rank 1. Oh, this is for well, at least for HHG, but plus, okay, color, if you want the really colorable. Okay, this is assumption that doesn't need to be made for product. It's automatic, it's trivial. But okay, but all the examples, there are some examples for HHG, but they're rather artificial, which are not colorable. So all other examples are colorable. In particular, the mapping class group is colorable by results of Besvina, Bromwell, and Fujiwara. Although I should say that for the mapping class group, this particular question of automorphism is not interesting because the automorphism group of the mapping class group is finite. But there are other related questions for which this will be interesting even for the mapping class group. And okay, I need also, okay, I need it will be this now, weakly acylindrical action on factors. On factors or domains in the case of HEG. Okay, so this is, and I don't know, this technique, it may be applied in other places, but this was my goal. That's it. I finished that. Yes. Actually, yeah. Okay, to construct a Makanian-Zborov diagram in this setup, either for homomorphisms or for automorphism, this is, there's a work of Daniel Groves and Michael Hall on acylindrically hyperbolic groups. Or anyway, anyway, basically there were techniques that are essentially sufficient to construct a Makanian-Zborov diagram, both for automorphisms and for homomorphism. The thing is, again, the thing here, first of all, the hard work comes after the diagram exists. For HHG, the diagram is slightly more complicated, but anyway, yeah, it exists. But this is the first step. The main ingredients here, which I knew, at least for me, is how to exhaust this canonical information from something which is completely not canonical. The diagram is not canonical. Okay, without JSJ, there's no way to make it canonical. But the real new ingredients here is how to start from the diagram and exhaust from it the structure of this just a composition with certain canonical properties. Where? What was before? It's not okay. These are not limit groups over free groups. These are limit groups in this context. Okay, so they are finitely generated groups in general. There's definitely no reason that they will be finitely presented. Even on hyperbolic groups, these limit groups are not finitely presented, so there's no reason. They have a geometric structure, but relative to some subgroup that somehow sits in the, if you want, the bottom of this tower, and on this I cannot say much. But somehow for automorphism, this group is also not important after you have all these constructions.
This kind of scheme, to study the conventional groups other than the open group?
Yes, I don't know. You should ask Mahan. Yeah. No, I don't have offended.
Where the extra factors of these equilibrium groups come from?
Where does what? Where these? Oh, this one. Yeah, these are precisely. You see, this is like, okay. if you look at the hyperbolic group, right, there are no interesting virtually abelian groups there. But even if you look, well, you can apply this for any finitely represented group. But if you look at limit groups, for example, in their JSJ, there will be vertex groups which are for limit groups over free groups which are just free abelian, and they have a subgroup of automorphisms that fix the edge that or the edges that connect to them. These groups are precisely, well, here it's generalized because okay, these are virtually abelian, but precisely because there are vertex group here which are virtually abelian, and they have automorphism relative to the edges, in general maybe several edges that connect to them. These are part of the. This is part of the modular groups, kind of canonical automorphism that one needs to include in order to, how to say, to associate the group of automorphism with this graph of groups. Okay? They don't appear in hyperbolic groups just because they don't exist.
So, at least close to some of the issues that motivated you. What do you think at this point about the Hopf problem for compact non-positively complex?
Okay, I'll answer that again. I'll answer for HG. Okay, for HG, I'm convinced that it's open. For HG, with the extra condition that I put, it must be open.
Answer my question.
Say it, make an answer. You can't hear it, but I can't.
Be prudent before about it.
No, I didn't think. No, you see, the whole approach that I took here, right, in order to study, was through these HEGs, and for them, I'm convinced that in fact even stronger properties should be true. You know, many properties that hyperbolic groups we know have can now be, or could have even before. You know, people can try and lift them to HHGs. The Hopf property is one of them, and the Hopf property should be true. No, but you know.
Other questions? Let's thank you.